Okay, thanks a lot for the invitation. It's my pleasure. It's a really interesting event. Thank you. So I'm going to talk about an NLP task and how we can teach computers to analyze text and predict judicial decisions. And, well, this is a list of collaborators. So let's start with some background. I mean, I saw previous talks started with a neural network, so I didn't know what to anticipate, so I started with some definitions here. When I say artificial intelligence, I just mean using methods from machine learning and natural language processing. So machine learning is defined as the subfield of computer science that gives computers the ability to learn from paradigms without being explicitly programmed. And natural language processing is the subfield of computer science, or let's say artificial intelligence, concerned with the analysis and interactions between computers and human languages. So if I mention AI, again, I just mean methodology and methods from these two areas. So 55 years ago, an American lawyer published a paper with the title, What Computers Can Do, Analysis and Prediction of Judicial Decisions. And in his paper, Lawlor actually argued that in the future, computers using data and probabilistic methods would be able to help lawyers and analyze cases, data from cases, actually to predict the judicial decisions, the outcomes of what court decided. So that gave rise to an area called AI-assisted judicial decision-making, and I'm trying to be very careful by using my words here. I just say AI-assisted. So what I mean by AI-assisted judicial decision-making, building data-driven methods for automating tasks related to legal advice and representation. For example, a law firm has a lot of data, a lot of textual data descriptions about previous cases, and they want to predict if they're going to win a case for a new customer or how much this case is going to cost. Also, from the court's perspective, a court could use an automated system for judicial decision-making actually to predict the outcome of a new case. And why is that important? Why should we care? First of all, we can build assisting tools to rapidly identify previous cases and extract patterns which led to certain decisions, given a new case. And also, we can build automated systems that could assess whether someone has got chances in filing a lawsuit. So you can save a lot of money and provide and improve access to justice. Also, the third point, which I find most important because it's more like an academic goal, is to help legal scientists to understand judicial decision-making in a way that machine learning and natural language processing and all these AI methods are used in other disciplines, for example, in health or in biology and social sciences. There are new areas of research called computational social sciences and computational biology, even computational health. Colleagues in UCL actually work on computational health. Also, from the court's perspective, prioritizing the decision process in cases where violation seems very likely is very important. And also, that could help us dealing with massive delays in judicial process due to vast amounts of cases. Courts have huge backlogs of cases that have not been decided. So if you have repetitive cases that are similar to previous one, then actually you can have a system say, well, these cases look like those that we have tried in the past. So there is previous work on this field, mainly focusing on the US Supreme Court, building statistical models that try to predict the votes of judges in the US Supreme Court using non-textual information. So there is a bunch of work here from the 50s up to 2012, people from LSE in London. And what they actually do is basically they use some manually crafted features, for example, the nature of the crime, the gravity of the crime, or the preferred policy position of each judge, because in the United States, you know who the president that appointed each judge, if he's liberal or conservative. And well, what is the problem with that is that these manually created features need human experts. So you need to have lawyers and legal experts that can decide what is the nature of the crime and what is the gravity of the crime. And also, this information is not available prior to the decision. So you cannot actually extract this kind of features before a decision has been made. Therefore, we decided to take a different approach, and we said, well, there is a vast amount of unstructured information, usually in textual format out there. Can we use it to predict judicial decisions? And when I say textual format, textual information, I just mean facts that are relevant to the case, and also legal argumentations of the two parties that are involved in a particular case. Also represented in textual format. We didn't use any particular form of logic and so on. It's just raw text. So how we did that? First of all, we defined a predictive task. So we wanted to predict whether a particular article of the European Convention of Human Rights has been violated. Sorry for the acronyms here, I should have mentioned. So we focus on predicting decisions of the European Court of Human Rights. I'm going to give you some information about that. Given only textual evidence extracted from a case. So the input is the text of a case, and the output is no violation. So in the previous talk, you saw that the input in the machine translation system was text in a particular language A, and the output was a text in language B, let's say. Here, the input again is text, but the output is different, is no violation and violation, well, represented with some numerical values. So what we do first, we have to represent our text into a format that can be read by the machine learning algorithm. And to do that, we transform it, and I'm going to show you in a bit. But let me give you some details about the European Court of Human Rights. I'm going to go very quickly. It's a major international court, and set up in 1959 by the European Convention of Human Rights. It's not an EU institution. It's more broad. It covers 47 states with 800 million of population. So there are countries like Turkey and Russia included in the European Convention of Human Rights. And usually, individuals go against states in the European Court of Human Rights. So why we did our research on that court? Because, well, it's very interesting. It involves human rights cases. And second, there is publicly available data, textual data that we could have access from the court's database. And also, there is a well-structured case format, so we could extract the text under its particular section. So what is this case structure? Usually when you have a case, you start with a procedure. So what is the procedure followed in a particular case in the domestic court before that case came to the European Court of Human Rights? And then there are the facts, circumstances of the case, and relevant domestic law. Then in the third section, there are the merits from parties, they call it the law. And finally, in the fourth section is the decision. So in our experiments, we just use text from the first three sections. And we filtered out any particular sentence or piece of text that it was subjective, or let's say the judges of the court made some subjective opinion. The court believes, or so on. So we filter out all this kind of information because we wanted to make sure that our textual data is as close as it can be to an information that a judge can have in front of him or her before makes a decision. So how that looks like, I'm going to go through quickly. So here is an example of a case, Veltseva vs. Bulgaria. And you can see it's like very general information. The case originated in an application so-so. The applicant was represented by X. So we just extracted this text. And the same from the facts, the circumstances of the case. The applicant was born there, and so on. Same for the law. And here we just extracted the outcome right? The decision, if there is a violation or no violation for a particular article. We didn't use this text for the prediction. And we built a data set for Article 3, 6, and 8. Why? Because we found most cases in these articles. So in Article 3, we found prohibits torture and inhuman and degraded treatment. We found 250 cases. Article 6, protection to the right for a fair trial, 80 cases. And Article 8 provides a right to respect for one's private and family life, 254 cases. So in total, we had something like about 600 cases. So we split articles into two equal classes, violation and no violation. And why we do that? Because we wanted to make sure that we don't give to the algorithm information about the volume of violation and no violation from previous judgments. We wanted to have a 50-50 baseline, because of course the true baseline is like 90-10 or 95-5. Everything gets a known violation. Only a few articles are violating the actual articles of the convention. Well, and a caveat here is that these are only theoretical, unbiased transcripts summarizing the case. So if we want to have, if we had access to the actual applications formed from the applicants, that would be the perfect experimental setup. So how we represent text. Here, we don't use neural networks because we don't have enough data. And also, the most important is that we care about interpretability. We wanted to see what are the most important features that the algorithm find to predict violation and no violation for each particular article. So we constructed two traditional sets of features in natural language processing that actually most of the papers used before 2013. Well, we still use. So this is contiguous word sequences called n-grams. So imagine that if you have the text a cat sat and you want to extract n-grams, what you do is basically you just process the text and extract any particular unigram, a cat sat. And then if you want to extract bigrams, a cat, and the trigram could be a cat sat. 3 words. Okay. And also, we built clusters of related words, and we call them topics, because in that way, we want to narrow down the feature space. We wanted to do dimensionality reduction, but not using PCA, because again, it's very hard to interpret the latent dimensions. So we wanted latent dimensions that are interpretable. So we clustered together words from our training data. And as you can see, here is a topic. And what we do to represent our text, we just count how many times we find each word for each particular topic in our case. So each case is represented as a vector, and each element of a case vector represents a feature. That could be an n-gram or a topic. And as I mentioned, each element is weighted by the number of times the n-gram or the words in a topic appears in the case. So how does that look like? We train a standard traditional linear support vector machine classifier. And what does it do? So let's go back to our feature space. It's very high dimensional and very hard to visualize, right? Because we have all these words from the n-grams and the topics. But let's say we have only 2 features, good and bad, and we try to predict if there is a violation in a case regarding detainment conditions, right? So if you map, what we do, actually we use the good and bad words, the frequency, as coordinates, and we map them in a vector space. And what we expect is that, let's say, cases about violation will be mapped very close by in that space, because they have high frequency for the word bad and low frequency for the word good. And on the other hand, cases that are about non-violation will be mapped close by, because they will have words about good and not very high frequency for the word bad. Okay, imagine that in a sentiment analysis setup, if that's a better example, you want to predict the sentiment of a particular movie review. You expect that your reviews that people that like the film, the reviews will be there, and the others on the left-hand side. And what we want to do is to find a hyperplane that separates these cases. And this is what the support vector machines do. And how we account for interpretability, basically, you can measure the distance of each particular case to the hyperplane. So you get a weight. So giving a supervised, so we call this supervised learning, and I'm going to give you an exam analogy, but very quickly. Imagine that you want to prepare for an exam in a module, and your training data consists only of all the available past exam papers. During training, you just learn by studying past exam papers. You can test yourself by holding out a number of past exams as a development, just to check if you have learned something. And the evaluation is performed on the exam day, which we call test data. And your score is computed by your examiner. And this is actually the experimental setup in every single text classification or supervised machine learning task. Even if we had used a different classifier, such as a neural network or, I don't know, a logistic regression around the forest, the experimental protocol could be the same. So we split our data into training and testing sets, 90 for training, 10 for test, and we repeat the experiment with different data splits, 10 different data splits. We call that tenfold cross-validation. And during training, the classifier learns from cases and the court's decision. And during testing, we just give the classifier as input case vectors from the test data to make a prediction. And then we just map this prediction with the actual judge's decision. So how we evaluate? We just measure accuracy on this tenfold cross-validation, how many times the classifier matches the court's outcome. And here are some results. Basically, what we learned, well, I have a lot of numbers here. Just focus on the circumstances. It gives the highest score. And that means that judges' decisions correlate with the facts of a case and not the legal argumentation section. Also, when we do dimensionality reduction and we use more abstract topics to represent our feature space, our cases, then we get even better performance, and the combination actually gives something extra as well. So on average, we get a performance of an accuracy of 79% across the 3 articles. So here is what are the most important topics on Article 3 for predicting violation, the top 3, and the bottom 3 for non-violation. Ranked by the weight that we obtained from the linear support vector machine. So just to sum up the findings, the circumstances subsection is the highest predictive accuracy against the low subsection, and that gives some sort of empirical evidence to the debate between realism and formalism in the legal theory, that judicial decision-making is significantly correlating to the stimulus of the facts. And also the topics appear to correlate with trends and patterns in the case law of the European Court of Human Rights. And that was actually identified by our lawyer colleague that was collaborating with us in that paper. So, limitations of these models. And, well, I mentioned here some things that could apply to any machine learning model. ML models only learn correlations and existing biases in the data. Other speakers actually mentioned that before. ML models do not understand language or meaning as humans do. Data can change over time. Legislation can also change. So basically, if you use prior data to predict future, prior cases to predict future cases, basically, if legislation changes, then the result, the outcome may change. And we have to make sure that our automated systems account for that. Also, we cannot take the human out of the loop, and that's why I say AI-assisted judicial decision-making. These models can be used actually to help humans to make more informed judgments, because they might have lost some sort of information in the process of making their decisions. Also, transparency is very important. Reproducibility, open source code when you build this kind of models, data availability and privacy. So if a law firm, let's say, has access to millions of data and builds a model that then productionized, then I don't know how that could be good or bad. Access to computational resources. For example, training neural networks for any particular predictive task, it requires a lot of budget, big budgets, because you run on the cloud using expensive machinery. And finally, model interpretability, causality, and giving explanations are very important in this domain. And also, I will finish with a question. Can such models be used in production, as we used to say in the corporate environment? I don't know. There are further ethical implications there, but I'm not the expert to answer that. Thank you.
Thank you very much. We have 5 minutes left for questions. Yeah, I see you in the corner, and then the next one.
Thank you. So my question would be, is there any attempt to find the causality, or could you probably introduce some of them approach to understand the causality?
Can you repeat the question? At the beginning, I lost that.
So you mean one of the problems with the machine learning approach is that we lack of kind of causal inference, something like that. So is there any approach that's try to learn causality through machine learning?
Of course, there is work on causal machine learning. We haven't considered for this particular work here. But let's say, if I can answer your question, we found out that we used actually the respondent country as feature. So, for example, if I go against Germany or against Greece or against Russia, we found out that if you go against particular countries, there is a higher chance to get violation, because in the data, these countries actually have a lot of violations. And that appears in the text. So how we can actually do a causal experiment, probably we could actually replace the text mentioning particular places and replace it with, I don't know, country, X, and then retrain the model and see what performance we get.
Yeah, thank you very much. It's a really interesting use case, I think. But imagine this, you take a corporate identity, and they train a model to 100% somehow. Then they have a new case, like a client case. They use this model, and they see they have like 10% to win it with their argument. They change their argument so that they get 100%. Well, I mean, this would be huge. Could it be done, or am I missing something?
It happens. Yeah, that's a very good question. It happens all the time, and it's called domain shift, right? In machine learning, for example, it's very good point. Yes, it may happen. The model will fail, but what happens? Let's say in a question answering system that basically you ask questions about football, and then you try to, let's say, transfer that in the US, and you don't get questions about football. Probably you get, but they don't mean football, right? They mean American football. Again, your question answering system will fail, let's say. So it's a very, very important problem, how it can be solved with online training, updating your training data consistently. But again, you're not going to be 100% sure that you will get the correct answers all the time.
Is there another question?
Thanks for your talk. I would like to ask you about, I don't know if I understood well, but when you talk about decision making, you're obviously talking about binary system, right? You're using a binary decision as a binary model, so it's either or. But hold on the graphic that you showed us, you're talking about this zone in between, right? They're like a differential, which is where, can you bring up? Never mind, I remember, I don't know, people remember, I remember the graphic, right? And I was interested in that zone, because obviously, first of all, the question about the transformation of law into rule-obeying behavior is an historical moment, okay? So the kind of assistance of computation or numbers to the judicial system goes back to the 30s. In terms of, within the judicial system, how one law from truth becomes calculation. So you have this shift that has already happened historically. What is new now, you talk about supervised machine learning. That's your argument, I guess, that we need supervised machine learning because this zone in between is where, the system, the decision is not either or, but is content, meaning, and so on. Well, if you look into machine vision, you develop machine vision algorithms, the point is exact, or if you look at the tendency of automation, which is ubiquitous, it's going to get everywhere else, the tendency is precisely to create systems that are automated enough so that you don't need a human, but the system are able to work exactly in that zone in between. Have you seen anything about that? Or is your argument for assisted machine, supervised machine learning something that can actually help not to just fall into this binarism? I'm not sure. Sorry.
So I have discussed this very good point. I have discussed that with judges and lawyers that are, let's say, more experienced and experts in that domain. And what I see is that, yeah, I would like to have the human there, if you ask me personally. And when actually a system like that makes a decision, then it's just only to inform the judge. Probably the judge made his own or her own decision, and then it says the model says, well, probably there is a possibility here that there is a violation or non-violation with some sort of uncertainty. And then just look on these cases because they seem very relevant for predicting violation or non-violation, and then just take a look and see if you agree or not with what the system says. The other point, well, it's not always binary. We formalized here as a binary task. It could be a regression task where we have a continuous scale that we make the prediction. And for example, we could use the votes because again in the European Court of Human Rights, you can get the votes from the judges. So you can say, well, it's 5-2, 70%, I don't know, 60% violation or non-violation.
Thank you very much.
Cheers, thank you.